Okay, hello everyone. In this video, we are going to calculate activation energy from imaginary part of complex impedance, that is your Z double prime and modulus M double prime data. Okay, so let us start. In this video, we are going to discuss procedure to calculation of activation energy from Z double prime and M double prime data. The activation energy will be evaluated or calculated by considering Arrhenius relation or equation. According to this relation or equation, here F max equal to F naught into e to the power minus EA by KT. Here F max is the frequency at which peak observed, EA is the activation energy, F0 is the pre-exponential factor, is a constant itself, K is the Boltzmann constant, value is your 8.62 into 10 to the power minus 5 electron volt per Kelvin, T is the absolute temperature in Kelvin scale. Here you can see F max is nothing but your frequency at which peak is observed. Suppose we are going to consider Z double prime data. This is the frequency versus Z double prime at different temperatures 30, 50, 75 and 10. So this black color is belongs to 30 degree here. This is the peak observed for this 30-degree temperature. Corresponding frequency is nothing but called as your frequency max here. This frequency will be called as frequency max. For 50-degree, this frequency is called as your frequency max, and this is your frequency max or F max. Okay, likewise, if we are going to consider M double prime data, this one, this one, this frequency here, peak we observe. For this peak, this is the corresponding frequency. For red one, this is the peak corresponding frequency somewhere over here. Okay. Now, how we are going to calculate by using Arrhenius relation, that we are going to discuss in this video in detail. Okay. Here, the Arrhenius equation is this one. I written over here. Just take natural logarithmic both the side of this equation. Ln F max will be equal to ln F naught e to the power minus EA by KT. Ln F max will be equal to ln F0 here, ln A into B, that means ln A plus ln B, ln A means F naught plus ln e to the power minus EA by KT. So here this value log of exponent to the power x is nothing but x, that we know, right? So here exponent to the power minus EA by KT, so the value will be minus EA by KT only, and this one ln F naught I written C because F naught is a constant, so ln F naught another constant, here I written as C. That implies ln F max will be equal to, here I just modified this equation for our simplicity. When we are going to calculate with graph in origin, at that time it is required. For simplicity, here I multiplied 1000 in the denominator and numerator. So EA by 1000 into K into 1000 by T plus C. Let this is your equation number 1, right? Now consider a line equation. Y equal to mx plus c, the general line equation in our xy plane, right? Let this is your equation number 2. Now just compare equation number 1 and 2. What we can found here, m is nothing but this value minus EA by 1000 into K. M, here m is nothing but slope for a line. So m or slope, if I will compare equation number 1 and 2, the value will be minus EA by 1000 into K. And here x value, if I am going to consider x in equation number 2, corresponding value in equation number 1 is your 1000 by T, and y is your ln F max, y equal to ln F max. Here this slope, if we can calculate, then EA activation energy, what we intend to find out, that EA will be slope into 1000 into K minus, here suppose I found slope value m, so EA will be how much? EA will be minus slope, that means m into 1000 into K. Okay, So how we are going to evaluate or calculate the slope? That slope will be automatically calculated by origin software. We are going to use the origin software to find out the slope. Okay, what we have to do in the origin software, we have to take ln max, sorry, along x-axis we have to consider 1000 by t. Here x we have to consider 1000 by t, and along y-axis we have to consider ln f max. So for each 1000 by t we can get ln f max 11 data like this. Okay, by using the origin software, if I will fit these data point, then automatically it will be fit by the linear fitting that we are going to discuss, okay, in the origin platform. So it will be automatically fit these data, and origin software origin software will be automatically provide you the m value. Okay, so here if we got the m value, then ea will be equal to minus m into 1000 into k. So here you can see from the line we can observe from this figure particularly, the slope will be negative. Here it is inclined like this, so obviously slope will be negative. When after fitting with the help of origin also we can get the negative slope. So ea will be how much? Already minus is there, slope will be minus, so it will be slope value whatever the origin software will be provide to us into 1000 into k value is your what? 8.62 into 10 to the power minus 5, and this will be electron volt in the unit electron volt, or this value is your how much? Slope into 8.62 into here 10 to the power 3, 10 to the power minus 5, so 10 to the power minus 2. So this will be a required slope what we can found by doing this much work. Okay, now we are going to go on the origin platform. Okay, here this is the origin platform. Already I have the two data. This is the frequency versus z double prime data at different temperature. Here at 30 degree this data, at 50 degree, 75 degree, 100 degree this data I have, frequency versus z double prime. And this is your frequency versus m double prime, that is your imaginary part of modulus. Okay, m double prime. And if I'm going to plot this one, how I'm going to plot this one? Here just wait, I have to delete. Just select these columns and click over here, it will come like this. Okay, you just zoom it somewhat, and here this one along x-axis is your frequency. In this data, this is your frequency data, right? Frequency, and along y-axis your z double prime, right? Z double prime in ohm. The here z double prime will be in ohm. So here to identify the peak clearly, you just to do the log along x-axis of this graph. So x-axis here go to the scale. Here you can found already it is in the linear format. You just click over log 10, apply, okay, and resize this one, rescale. So we can found clearly identifiable peaks at a different temperature. For 30 degree here is the peak, 50 degree here is the peak, 75 degree here is the peak, 100 degree here is the peak for z double prime. Likewise you can do for m double prime. This is your frequency, and this is your m double prime. M double prime, right? And take the log of the x-axis, then rescale it. So here we got the clearly identifiable peaks for modulus data, imaginary part of modulus data. This is the peak for 30 degree here. Here for the 50 degree, 50 degree is the red color, blue color is your 75 degree here, and this is the 75 degree. Okay, so here clearly we can identify the peak. So corresponding frequency you can measure by two ways. First we are going to do for the Z double prime data. Okay, Z double prime. Here what, you just click on this one, screen reader, click. If we are going to click on this peak, you can found x and corresponding y. So here I clicked on the peak, corresponding x is your what, 734242, around 7342 frequency, but may not be it is exactly this value. For that you have to search in the table. Okay, here in the graph we found what is the value, value is yours around 7000 plus. Okay, so you go to the table. Here you can see here 6533, it is the value is your 12873. Then it is increased, then it is decreased. See, 7058.9 value is your 12,881. Then after it is decreased. So this is the peak value. This is your F max for 30 degree. Okay. So what we have to do, we have to consider here, we have to consider what, along x-axis 1000 by t, along y-axis ln F max. So first we have to insert another worksheet over here, and we have to consider what are the temperatures. Temperatures is 30, 50, 70, 100. So here we have to make a column for temperature first. Temperatures are your 30, 50, 75 and 100, right? 100. Okay, this is your F max column. F max. So for 30 degree F max value is what, this one. You just copy it, copy and paste over here, right? Okay, next we are going to go for 50 degree. So here for the 50 degree, the peak is around what, 8900. You just confirm from the table, 8900. See, this is the 50 degree, this is for the 50 degree. Here this value is increases 9714, 9738, again decreases 9733, decreased. So this is the corresponding F max for 50 degree. You just copy it and paste over here. Okay, likewise for 75 and 100 degree, either you can identify from the graph or you can identify from the table. 50 degree work over 75. See here, peak is shifted towards the right, towards the higher frequency side. So you have to search at the higher frequency for 75. 75 means here you can see 4707, then 477648, increased 4999, it is increased. Yes, it is increased. See, this is the highest, 4925 value is the highest for 75 degree. 4925, corresponding frequency is 19307, right? Before that it is less value, after that also less value. So this is the peak value and corresponding frequency is your this one, 19307. Just copy it and paste in the workbook 3. Pasted. Now we are going to find out what is the F max for 100 degree. Here you can see 2660. See here, 2649688085, then decreased. See, then decreased. This is 26, then 25 decreased. That means this is the max value, 3078. For 100-degree temperature, this value is maximum. Z double prime, here you can find the maximum value, 2680, right? 268 is, sorry, 2685. Before that 2680, after that 2682. So this is the maximum. Corresponding F max will be 30718. Just copy it and paste in the workbook 3. Pasted over here. So here we found temperature and corresponding F max. So here temperature in degree centigrade format, but we need along x-axis 1000 by T, where T is in the Kelvin scale, right? So how I am going to convert it? Here I am going to write this column. I am going to convert like this, 1000 by T K in Kelvin. So what I have to do? This one here I have to do, select this column, click right click on your mouse, click on this one, set column value. Over here a pop-up window will come up like this. So here what you have to write, 1000 by bracket starts 1000 by temperature, but temperature should be in the Kelvin scale. Here column A, whatever the data or the temperature we have in the degree centigrade. So column A plus 273. Now this denominator converted to Kelvin, 1000 by Kelvin. Okay, just apply and okay. Now here we constructed our x-axis. Here 1000 by T in the Kelvin scale, right? This one along x-axis work our over. Now along y-axis we need ln F max. This is easy. So what you have to do, you just consider this column, click over here, again click right click on your mouse, set column. This column we are going to set as what? ln of column B. Okay, so here you have to write ln bracket start column B, bracket closed. Bracket is most important here, right? Okay, or you can consider this formula also. Here it is not there. Difference between row, compute, cumulative sum, etc. But you can write directly itself like this, whatever I written, ln column B, bracket in bracket column B, you have to write, apply, okay. So here we found ln of this column or ln max. Here we calculated what? ln F max, right? So this is our x-axis and this is our y-axis. So here I am going to suggest to you that you just write this whatever you want to write, you just write here, okay? Then it will come in the graph itself. So along y-axis what we taken, ln F max, and along x-axis we considered 1000 by T. Okay, now you just select these two columns. This is your x-axis, y-axis, and click on this drawing button. You can find the points. Along x-axis we considered 1000 by T, along y-axis ln F max. Now we are going to fit this data as linear fit to finding the slope, right? So how we are going to do with the help of origin? Here analysis tool is there. You have to click over here, you can find fit. So many fittings are there, but here we are going to use linear fit. Okay, before that you have to select what are the points should be included for fitting. Here we are going to use all the points, so I have to select all the points over here. Consider this button, region data selector, this button, region data selector. Click over here and select all the points like this. That means the points from here to here and in between these two end data points, all points are selected. Now you are going to go for fitting. Click over analysis, fitting, then linear fit. Then either you can go for the open dialog or last used. Last used means whatever the open dialog you already created. Okay, we are going to go for that one, open dialog. So no need to change anything over here. Input data, okay, graph, okay, no need to change anything. Now click over okay. Okay, see, the origin automatically fitted this data as linear fit, and a calculated value it will provide to you. This is the calculated value. So here this is the general equation of y equal to a plus bx. A is the constant, we should not bother about that. We should bother about b value. B is the slope, already written. Slope is nothing but b, and here b maybe written or not, not written. Okay, b is your slope. Here how much you got the slope, how much you got here for this data, you got the slope is your minus 2.497, up to 3 digit you can consider, minus 2.497. Okay, now we are going to calculate what will the activation energy for this one. Here already we have see what we have to do. The activation energy I told here, this is the equation. Activation energy is what, minus of minus m, sorry, minus of m 1000 into k, and here what you found slope is negative minus 2.497. So final expression should be like this, ea is equal to, see, if I will put this value, m value is negative, automatically it will be positive, right? So m value I have to put just over here 2.497 into 8.62 into 10 to the power minus 2. Obviously it will be in electron volt. Now we are going to calculate what will be its value. Here 2.497 497 or 479, 497, yes, 497 into 8.62. we found the value is your 21.524. 21.52, you just consider 52 into 10 to the power minus 2. So finally we found 0.2152 electron volt is your activation energy. Okay, from Z double prime data. By using Z double prime data, considering 4 temperatures, we found this value 0.2152 electron volt. Okay, likewise you can do same procedure, you can do for frequency versus m double prime. By considering frequency versus m double prime, you consider another worksheet. On the worksheet you just you have to find out these values, right? You have to find out these values here. In which way I have been explained, same way you have to do for m double prime also, same way. That means m double prime, this is the m double prime data. See, in your in this m double prime data, carefully you have to search for that. So here you can see in graph in graph, this point is at what, 21,000, around 21,000, frequency is your 21,000, and the m double prime value is your what, 1.56 around. So for that I have to search in the data sheet exactly what value. 21,000 means here this, around this value you have to search. Here 1.51, 1.54, 1.55, 1.56, 1.56, again it is reduced 1.55. So here this value 1.566233, so this value is the highest value, m double prime peak value, and corresponding frequency is your 2381. So you have to just uh, uh, copy this one and paste over here. And these are the temperature, 30, 50, 75 and 100. Okay, likewise for 50 degree, what will the value, here this one peak is here 42,000, around 42,000 you have to search. 42,000 means just come to here, 42,000, 1.58, 1.58098, 1.57. See, this is the maximum, then it is reduced to 1.57. So before that it is less value, this is the maximum value, 1.58098, 1.58063. So this is the f max, sorry, maximum value, peak value, corresponding f max is this one. You just copy it and paste over here, for 75 you have to just search 75. 75 means here you have to click carefully, you have to do this. Okay, here the peak observed at this point around 83,000. We have to check on the data sheet. 83,000, 83,000 means nearby this point. Here you can say 5617, 5687, this one, then 1.577. Yes, this one 1.577, then it is 1.56. Okay, so this one is the maximum, m double prime maximum, corresponding, just wait, this is around 1000. This one, yes, again I have to consider the graph, around 1000 it will come like this here, no? Yes. Okay, so on the data sheet this value is the maximum peak value, and corresponding f max is this one. Copy this one and paste over here. Now we are going to go for 100. Like this 100, you just check on the graph. Here all it is in the increasing format, so you could not found the peak value. You have to take this value. Okay, just after this one, 114806, 114806 you have to write 114806. Why I done this one? This is the most important point that you have to consider. We are trying to find out the corresponding f max of the particular peak. So here the peak is this one. This is the peak. I am going to show you the zoom. This is the peak. Okay, after that some other peak will become at the higher frequency, we do not know, but how much data we have for the 100 degree centigrade, this is the peak. But here you can see this 100 degree data continuously increases, but other data for 30 degree, 50 degree, 75 degree increased a maximum, then somewhat decreases, decreases, but this 100 degree is just slightly given what, a small hump, and increases. So here this is the corresponding peak just after the peak of 75, observed at here around 1000, right? And peak of 1000 means here. Okay, peak of 100, obviously it will observe just after that one. Means around here 11,70703 you can consider, or what I consider 11,4806 also more or less correct, no problem. So approximately we have to consider this value for this type of data where we could not found exact peak value. At that point we have to consider like this. Click here, just nearby this one. Okay, this value you have to take whatever I written over here nearby this value. Either this will be 11,048 or 11,007, sorry 11,4806 or 11,7703, whatever. Okay, now same procedure, you have to just click over here, set column as 1000 by column A plus 273 bracket closed, apply. Okay, then ln max, right click on this column, set column value as ln of column B, bracket closed, apply. Okay, so here we found this is the x-axis data and this is y-axis data. You just select both and plot the points. We have to consider all the points for our fitting. Select all the points by considering the region data selector and go to the analysis, go for fitting, linear fit, and just click on last use, because last time we done the same same by considering the linear fit. So you just click over last used, so it will automatically fit the data and it will provide the slope. It will be approximately same value. Here you can see from Z double prime data we found minus 2.49 and here we found minus 2.66. So if I am going to consider this one, this value, the what will the activation energy? Here you can see activation energy is nothing but your what, the m value into 8.62 into 10 to the minus 2, right? So here 8.62 into this value 2.66, right, into 2.66, this one 8, suppose we are going to consider. So we can get 22.99 and 10 to into 10 to the minus 2, no, into 10 to the minus 2 is there. So we can found the value will be equal to 0.22. So here we found 0.21, here we found 0.22. Okay, same value we can get. See, this is the way, this is the another way by considering m double prime and z double prime, but same sample data, no. So same sample data and we considered over here the same temperature range 30 to 100 here in z double prime, in m double prime also 30 to 100. So obviously we can get the activation energy is your around approximately same value. Okay, so here activation energy from z double prime, how much we found here, this value, 9 activation energy we found this one 0.2152 electron volt, right? So here from z double prime activation energy how much we found EA 0.22 you can write itself 0. Okay, 0.225, sorry 0.2152, okay, 215 you can write 215. Okay, you write 52 electron volt from z double prime, from z double prime data. Okay, similarly you can from z double prime data by considering Arrhenius equation we found activation energy is your 0.2 2152 electron volt, and from m double prime we found approximately that value around, how much we found, 0.22, right? 0.22, approximately same. Okay, both the data belongs to same sample, so only for that in the same temperature range activation energy will be same, we can found same. Okay, so at the last I want to share a important information with you, which is most important here. The Arrhenius equation is written as like this in general, okay, but in various research paper, you can found this Arrhenius equation is written as like this: F max is equal to F naught e to the power plus EA by KT. Why it is written? I'm going to tell to you that here. If I'm going to consider this data, the peak shifts towards the right side. Either consider your Z double prime or consider M double prime data, peak shifted towards the right side with increase of temperature, or peak shifted to higher frequency side with increase of temperature. But for all the sample, it is not so. It may be shifted towards the left. I'm going to show you one another data I have. Just wait. I'm going to show you. See, here another data I have with temperature peak shifted towards the left side. This is Z double prime data. So 30 degrees here. The peak is here, right? 50 degree here. Peak is here. 75. This is blue color here. 100 is your magenta here. Peak. So up to 100, the peak shifted towards the lower frequency side or left side. Even if from M double prime data also same. See, this is your black color belongs to 30, then red color this one, you can see peak shifted towards the left side. So peak shifted towards left side is nothing but your PTCR behavior, or positive coefficient of resistance. With temperature its resistance increases, but in this case with temperature resistance decreases. Okay, if resistance decreases, then the peak will shift towards the right side or higher frequency side. If resistance increases, the peak will shift towards the lower frequency side or left side. Okay, this is the general thing in a semiconductor physics, or in your complex impedance spectroscopy. This is the general. So here what I am going to say, suppose I am working in this data, a NTCR behavior, negative temperature coefficient of resistance, NTCR. That means with temperature resistance decreases. For that, if I am going to use this equation minus EA by KT, the slope after calculation from the origin, the slope will be found as negative. So this minus cancelled out and we found activation energy is your positive, right? Now you just imagine if we are going to consider this one, this data with increase of temperature up to 100 degree, up to 100 degree, that's peak shifted towards the lower frequency side. That means PTCR resistance increases data. If I'm going to consider this data, then you can found for that case where temperature your resistance increases, that means peak shifted towards the lower frequency side, the slope will be like this. Slope will be positive, m will be positive. We can get slope will be positive. Here I am not discussing in detail, I'm giving information to you. Slope will be positive. So if I put over here positive value, the activation energy at that time we can get what? Negative. So only for that, some research paper you can found, they also written in this format, plus EA by KT. Now, if I am going to compare these two equations, that is e to the minus and e to the plus ea by kt, there is no wrong that we are going to write e to the plus ea by kt if we are going to calculate the if we are trying to find out the activation energy. So here, if after calculation may we can get the activation energy positive or negative, but we have to consider the modulus value. Okay, suppose if I am going to consider this equation and I have to follow this procedure, then finally what will the value we are going to get? We are going to get the activation energy will be negative. This value will be negative because slope will be negative and this will be positive if I am going to consider this equation. So finally at the end we can found the activation energy will be negative, but energy could not be negative. So in this way we can think that may this equation is correct or incorrect, confusion will come in your mind. But don't be confused. Whatever the value at the end you got, you just take the modulus. That's it. You take the modulus. Either you follow this equation f max equal to f0 e to the power minus ea by kt and calculate with the help of this procedure, or f max equal to f naught e to the ea by kt. There is no wrong to write either this in your research paper, but at the time of calculating ea with the help of origin by fitting the data, you just at the final step you just consider the modulus of value, how much you got. Okay, here I am going to show you some research articles where this Arrhenius equation are used. Here you can see Arrhenius formula used as this one, your f max equal to f naught e to the minus ea by kbt, what we have been discussed. Okay, this is one of our research article which is published in 2016. Here we have been used as positive. Here plus ea by kbt, f equal to f naught exponent of ea by kbt. Another article I can show you here, also same positive we have been used. Here another article I am going to show you, some other article, f naught exponent of minus they have been used. Here this is one of my article published in 2020. Here I have been used plus. Here I considered the relaxation time. This tau is the relaxation time. Using the relaxation time also we can find out the activation energy, and also DC conductivity data also we can found the activation energy. Here RNS equation written as plus ea by kbt. Here another paper what we have been published in 2017. Here also we have been used plus relaxation time, we used tau naught exponent of plus ea by kbt, right? So with this conclusion I can say that you just calculate with this procedure. Either you can take plus ea by kt or minus ea by kt, there is no issue, but at the end you have to consider the modulus value. Okay, okay, so this is all about procedure to calculation of activation energy from Z double prime M double prime data, complex impedance and modulus data. Okay, I hope this video will help you in your research work. Thank you so much for watching this video. Thank you.